Tuesday on San Oh, yeah, so they're all. So usually morning. Yeah. That's good. Read.
Yeah, exactly.
We gotta come up with a settlement.
Saying nonverbal feedback, yes, slow down, etc. from reactions to the bottom.
So,
Nice circles, kind circles.
man, that toolbar really is growing.
What toolbar? This here?
Right?
Yeah.
Actually, well, because you have to add more features over time.
There's notes
features,
and more.
and then it produces a market opportunity for somebody to want the version again.
Yeah, it's weird because
We
Zoom,
have this cycle of life.
I feel like Zoom was born bloated.
No, actually, the original Zoom was not that bloated. In fact, I think that's part of why Zoom took off is because they focused first on getting the networking quality or the quality of the video with large number of participants. Yeah, that was their primary focus, and that's why they. Because I remember the first time I joined a Zoom call it was like 2014 or something like that. It was a Zoom thing. When I could download something on this, and
Yeah, why it's 5 minutes.
and then suddenly it was like 8, 10 people on the call, and it was actually working. I was extraordinarily surprised. Nothing worked back then. Wow.
Well, now they want to compete with Microsoft.
What?
They want to compete with Microsoft now. They're trying to add all these features,
you know.
like note taking and whiteboards and all that, and chatting, channels, whatever. Yeah.
WebEx.
They have the money to do it, don't they?
WebEx, Cisco WebEx. You should never.
Oh, yeah. I downloaded it once and then uninstalled it just after one.
Yeah, mega form.
Okay, I think we can get started now. So welcome to today's Zoom meeting, or I guess our DLAB research meeting. Today we have Evan, who's a guest speaker. He was invited by Philip, and you'll be talking about programming by PBE, programming by example, and something really interesting. So I'm excited to invite him over. Yeah, we'll just get started. Feel free to introduce yourself more. I didn't get to introduce you in enough detail, but yeah.
Yeah, no, that all sounds good. Thanks for having me. Is this kind of like the HCI reading group or something equivalent, or?
Yeah. We gather around every Wednesday, and
Okay.
yeah, we have people in our lab who give talks and share their ideas, and also some external speakers.
Okay, cool. Yeah, so that seems like the right crowd. Yeah, so yeah, what I work on is kind of building instruction following agents, and to build better system that allow human to communicate to system kind of more intuitively and have the system respond in a human-like way, right? And so roughly work in kind of CogSci AI, and I definitely touch upon a lot of HCI topic, right? Because if you want to build interactive systems, like they have to ground out in human interaction down the line for kind of evaluation. So I'll get started. Is it possible to make the screen where I can see all the people in the room bigger? Right now I see Brian, huge face of Brian, and like a guy with a bottle with a blue cap. Like his face is huge.
I wish I could edit this like panorama mode to make it bigger, but I don't think I can.
Okay, well, it's okay. I'm used to seeing people in, you know, pixel level detail in this meeting, so it's no problem for me. Cool. So I'll get started. So yeah, the talk is on pragmatic program synthesis. The idea is to introduce you guys to kind of a line of research that basically allow synthesizer to disambiguate program. So in program synthesis, a problem is there are kind of 10 programs. They're all somewhat consistent with the example or the kind of the interaction that you have with the system, and they're all equally good, factually speaking. And so how do you pick the one that the user have in mind? Okay, so below is my Twitter and my email. So feel free to reach out to me and we can hang out. I think it'll be really fun. Okay. And so goal is to, yeah, like I said, to introduce to you guys the idea of pragmatic program synthesis, and specifically using rational speech act, which is a branch of simple equation from cognitive science to programming by example. And by applying this, you have, programming by example synthesizer respond in a more human-like way. And this approach is actually general, so it actually applies to any PBE domain. So you might find it quite helpful in your own work if you want to use it. And I'll be showing you how to kind of scale that into a kind of bigger space of programs and examples. Yeah, so those are the goal. I guess we want to start by introducing program synthesis a little bit for those of you who, I'm pretty sure you guys are familiar, right? Because you guys think HDAB, but I'll try to kind of explain anyway. Right? So the idea of program synthesis is you basically try to build a robot that translate natural instructions into programs that can be executed on the computer to produce some kind of desirable outcome, right? And so the first question we can ask is, okay, well, what kind of instructions are we talking about? And on the market, there are kind of two branches, right? The first branch is instruction using natural language, right? So this is, you could think of it kind of like a translation task where the user give natural language, basically telling you or telling the system what the program ought to look like, but stated in a more naturalistic way. And the system translate that into a program. And so basically generating code from language. I'm sure you guys have all used Copilot in your work, right? And the way it is trained is there is a large corpus of comment to code pairs exists on the internet, right? And then if you train a kind of a autoregressive model just on this corpus, you kind of get the translation from comment to code for free. And so that's generating code from language. But another way to specify to the computer what you want the program to be is by using examples, right? And input-output example actually show up quite often in programming, right? It kind of normally taking the form of test cases, right? Which is to specify the semantics of the program, right? So over this input, you should receive this output. And so instruction using example is quite a good complement of instructing with only language. So I'll give you some Autodesk example. Imagine you have some, bathroom stalls, and then you tell the system, can you move the toilet to the other side? It might misinterpret it and having these toilet who, face the wall when you're using it, which might be, pretty awkward. But if you just add one example, which is, can you move the toilet to the other side, like the first one I did, then it's kind of much more clearer to the system that they need to move the toilet to the other side, but also kind of flip it, right? So they're facing the right direction when you're having a poop, I guess. And so programming by example is, just a recap, is kind of like puzzle solving, right? You tell the system what is the input output that the program need to respect. And then the system have to figure out the program that map the input to these outputs, okay? And so this is kind of a summary, which is why might you still be interested in programming by example, especially in the area of large language models where, there's a kind of communicating program by a language has been kind of the dominant way of communicating program is it's actually pretty precise, right? So that when you give the computer a set of test cases, it's actually quite clear if the program is right or wrong from that specification. Hey.
I had a question, which is,
yeah.
I'm so excited about your talk because I'm really curious about what the latest is here. I'm several years out of date and a lot's changed. And one thing I'm curious, and I'm especially selfish because I hope that you're going to offer a solution that makes it possible for professors to program again. It's hard for me to understand from these examples because that's not something that I or most people I know would do on the left-hand side. And I was wondering, and maybe you'll get to it, what's the simplest example or the simplest instance of something that you know, one of us might actually want to do? Like, what's the simplest real left-hand side?
I guess it might be easier if you can tell me more about the line of work that you want to do with a computer. Are you
Like, I
using
guess
it to, yeah.
I think programming by example is very interesting. I'm not sure I actually would ever really do f of 2 equals 4 though. And so I'm
Yeah.
trying to understand what the simplest real left-hand side is.
You're asking what's the simplest left-hand side of something that look like this that's also somewhat realistic, I guess. Is that the question?
Yeah, you're right.
Yeah. I don't know, man. PBE has always have these like string manipulation kind of a vibe, right? So maybe like regexes is an example I would touch on later in the talk. But I think eventually we aspire to do just kind of test-driven programming, right? So when you write a piece of code, you write test cases or assertions. So those are ultimately the goal we want on the left-hand side. So whatever test cases you want to write about a general software, you might develop, or assertions about some property of the software. Is that like a reasonable answer?
Yeah, I mean, I guess from like the human side, what I'm really curious about is, does this approach, you know, either the language specification or the example specification, when is it a win over programming?
I see. I don't think it's ever a win over. I don't think programming is ever a win, right? I guess this is like very philosophical, but like, yeah.
Like, so for me, it would actually be easier to type f of x equals x plus 2 than it would be to type f of 2 equals 4 or a function that adds 2 to x.
Yeah, that's right. I think it would be silly to think otherwise. That's right.
I can attempt an answer. I'm trying to think about what is, what are the advantages of PBE versus PBD and stuff. And I think PBE is really good when you have inputs and outputs that are small, so that they're easy to type. But also B, there's a clear correspondence between them, and then this stuff does come up. It comes up like in like string manipulations, like if you want to convert a string to a date, or if you want to, for example, do a particular format of a date. You can give the example of here's my input date, and then the output that you're expecting is a particular format.
Yep, totally.
So like those kinds of scenarios where you have small inputs and small outputs, or at least small to type, like you don't have to give a large example or something like that. And there's a clear correspondence between them. Those tend to be the scenarios where PBE is really good.
But now with dates, that's a special enough case that you could almost just special case dates to work right in whatever your programming system is. You know, we have so many date types and they're so important in life that you could kind of special case that.
Yeah, but you can also imagine other cases too. For example, a lot of companies have serial numbers and there's a lot of information encoded in, for example, serial number.
Right, totally, yeah.
But those are very specialized to the particular company, so that would be the case.
I think in general, test cases, right? You guys all write test cases. I think those are ultimately what I want to put on the left-hand side, right? Like, can you come up with a program that has all these unit tests? So I'm sure you guys write unit tests. And so that would be like preferred. And in general, I do think input-output example or test cases or assertions kind of covers a very different space of intent than language, right? And in general, those two can be quite complementary. In the ideal world, I think you will primarily use language actually, as you would with another programmer, right? And I think typically people use example to kind of as a kind of like a catch case of like potential misunderstanding, right? So when people read like the spec in language, they kind of, oh, it could be like one of many interpretations, and the example are there to kind of fine tune of like, oh yeah, it's actually like this particular kind of implementation rather than the other one. But yeah, this talk will be kind of pushing the example to kind of encoding more information about your intent by doing some additional layer of inference. So yeah, so that's kind of the nature of this particular talk. I hope that's reasonable. Is that all good? Should I go on?
Go ahead.
Yeah. And so just to kind of spend a little bit of time talking about how a kind of PBE synthesizer work, right? So the idea is you input some test cases and output a program that has the test cases, right? And kind of the core to the system is a kind of a program enumerator that allow you to generate program from some space or distribution, kind of one after another. And then this kind of enumeration is really flexible. You could do it however you want, right? So we've been using kind of explicit enumeration from some grammar, right? Or you could use LLM with some kind of prompt and ask it for, with some temperature term, like output temp program that might work for these test cases. And then what you do is you just use the interpreter to check if this program has these test cases. And then you output like the correct program, right? So it's quite flexible and it's data free, right? It doesn't really require any training data, as long as you could generate program to check if they pass the test. And so one issue of PBE is ambiguity. So if I give you kind of the spec like f of 2 is equals to 4, kind of the human intuitive guesses are like 2 times x or x plus 2, right? But there could be some spurious program that also match the description of 2 goes to 4, which are these like strange expression you have on the right and the one that kind of ignores the input that just always output 4, which are kind of technically correct, but they don't actually match human intuition on what should be returned. And so the idea is, how do we kind of build a system that kind of prefer kind of intuitively the program on the left-hand side when there is ambiguous specification with respect to just being literally correct, okay? And so here I need some of your participation. I think it's really good that I can see the panorama view, so I can see if you raise hand. And so I'll give you some example on how human resolve ambiguity. And this is an example from Frank and Noah Goodman, the rational speech hack. So here I have 2 concepts, A and B. A is the concept which is the figure who wear glasses, and B is the concept of a figure who wear glasses and hat, okay? And so now I want you to imagine communicating to another person about one of those 2 concepts, right? And so the role play, your prompt, I guess, is if you imagine the role of you being a speaker, and then you're trying to communicate the concept B to another person. And let's say it's a binary choice, you can only say the word hat or glasses. And so I'll give you guys kind of some time to just digest that question for a bit.
Hat.
Definitely hat, yeah.
Okay. And so can I have a...
By the way, that's Greg's.
Yes and no. Grice has a kind of a axiomatic way of thinking about it, but RSA has a computational account of this, which I can explain. So I guess there's no more hand raised. Most of you guys think it should be hat, right? And so now I want you to assume the role of a listener, right? So imagine you heard the word glasses. Someone said, "Oh, glasses." And so which one of these concepts, or A or B, is more likely? I'll give you another, like maybe 10 seconds to look at it. Okay, so can I have a hand for A?
A, yeah.
Okay, so can I have a hand for B? I don't actually see the right-hand side of the room, but I assume nobody raised their hand, right? Okay. So essentially what we have done here is to disambiguate by reasoning about what the speaker could have said, right? So since we didn't hear the word hat, then it's likely that they weren't trying to communicate B, even though glasses is kind of applicable to both concepts, right? And so this talk is about kind of the RSA, rational speech hack, that account for these kind of phenomena, basically using Coxeye to explain these kind of phenomena by some kind of mathematical modeling, and then applying these kind of mathematical reasoning into program synthesis systems so that we might have program that disambiguate among multiple competing hypotheses in a way that's kind of human compatible, okay? And so roughly I'll go over about like 3-4 years of lines of work, right? And then these works actually covers kind of the natural question you might have with applying pragmatics to program synthesis, which is first I'll explain what RSA is, right? The computational model. And then I'll describe to you like this kind of next line of work is like, does it even work? Yeah, like, do you build a synthesizer with RSA? Do humans actually interact well with it? And the last two work is about how to scale that into bigger, more realistic domain like regex, or maybe kind of hope we aspire to, right? Input-output example and test cases. Okay. So let me first quickly describe what is Rational Speech Act. And so the kind of the short description of Rational Speech Act is that RSA is an algorithm, right? Given a particular communication game M. And what is M? M is what we call a meaning matrix. It's a kind of a 0-1 matrix where on the columns you have hypotheses, right? So for the game we just played, there are two, right? There's A or B. And then on the rows, we have utterances. And in the game we just played, we have hats and glasses. And in the entry, it's a Boolean table of zeros and ones, right? Where 1 means this utterance is compatible or consistent with the hypothesis, and 0 means they are kind of incompatible, right? So what the RSA algorithm will do is that RSA will input this meaning matrix M of a kind of a 2-player communication game, and output of the RSA algorithm is 2 probability distribution, a human-like speaker S1 and a human-like listener L1. Okay, so I'll describe the algorithm. And so we start with a meaning matrix M of logical consistencies, and then the result is basically a speaker that taking hypotheses such as A and B, and output an utterance such as hats and glasses, and also a listener that kind of do the reverse process, right? To be able to kind of recover the hypothesis from the utterance. Okay, and so cool. So RSA algorithm is kind of a recursive Bayesian algorithm, right? It's at the topmost level, it's a informative speaker that informative listener that recursively reason about a informative speaker that recursively reason about a literal listener. So there's kind of a handful. So I'll break it onto kind of like one step at a time. So let's start by describing the literal listener. The literal listener is kind of like the robot. So the job of a listener is a listener receive utterances and give distribution over hypothesis, right? So the robot, upon hearing the word glasses, will give kind of equal probability to the hypotheses that are consistent with the utterance glasses. So this is written as the equation, which is proportional to some prior over hypothesis, along with whether that hypothesis is consistent with the particular utterance. So on top of that, we build a pragmatic speaker that recursively reasoning about the literal listener. So to recap, the role of the speaker is the speaker input is a hypothesis, and then the speaker needs to choose utterance, right? Like, how should I use the utterance to describe this hypothesis? And the reasoning is I'm going to, as a speaker, use the utterances that's proportional to how likely is the literal listener going to recover my intended hypothesis. And so it kind of recursively reasoning about the literal listener. And so when I receive the concept with the hat, right, and glasses, I will think about, well, if I said glasses, then this silly robot might mistake it for like a different hypothesis. So I'm going to use hat. And we can do this like one more time, which is the pragmatic listener that recursively reasoning about the pragmatic speaker. Okay, so from a kind of calculation point of view, this is really a series of normalizing rows and columns, right? So on each one of the L0, S1, and L1 computation, you could do that kind of explicitly for small domains with just this matrix, starting with a 0-1 matrix. And if you normalize a row, you get the L0, you normalize the column, you get the S1, and you normalize the row again, you get L1, okay? And I just want to focus on kind of this last row here with the glasses, right? So you see how in L1, given the utterance glasses, it has kind of a preference of A over B, right? So this is kind of what we observed with the audience participation. And so it turns out that it's not just for this audience here. In general, they have shown this computation model actually match human behavior quite well. Okay. So that's what I say. As a recap, it's an algorithm that inputs M and outputs kind of two distribution that kind of are somewhat human-like and they play the game well. Do I have a question?
No.
Cool.
Yeah.
All right, so I'll go on. So now we know this algorithm, we're going to try to apply this to program synthesis, right? And the key question the big unknown is like, does that even work, right? That's like the biggest risk factor. And so I'll describe to you how that works. And this slide is the most important slide of the entire talk, which is a parallel between kind of communication and program synthesis, right? So on the left-hand side, we have a meaning matrix where on the column we have hypothesis, and on the rows we have utterances, and on the entry we have consistency between hypothesis and utterances. That's kind of maybe decided by some kind of logic, right? And on the right-hand side, we just kind of do the same for program synthesis, but on the column now, we have programs, and on the rows, we have examples. And on the entry, we also have a 0, 1, but that's derived by execution, right? Which is, does this program satisfy these example if you were to execute it? And so really, it's kind of realizing those two are kind of exactly the same. And so RSA algorithm, if you could run it on the meaning matrix on the left-hand side, which is simply a kind of 0, 1 grid of number, you could certainly run the same algorithm with program synthesis on the right-hand side, which is also kind of a grid of numbers, right? So the key idea is you take the meaning matrix of program cross examples, and then you run the RSA algorithm, and you will end up with a pragmatic, like an algorithm kind of a listener, which takes in examples and output programs. And then the idea is that you want to pair that with the end user, and then you kind of pray that this work better than if you don't do RSA, right? That's kind of the question. So some pro of this approach is that it really only requires a meaning matrix N, right? Which is actually well defined by the semantics of the program. So it should actually apply to most programming by example domain. And there's some support by Coxeye. And the unknown is we don't actually know if this will work. And so the idea is we kind of try it out to see if it works, right? So in this first kind of domain, we tried it on a programming by example domain that's not so big, but not so small, right? We have a grid lane DSL that basically generate the output of the program over all possible input, which is like XY coordinate, it generates kind of like a grid-like pattern. And so if you, and as an example, you could actually kind of declare to the system, hey, on this particular coordinate, you have of a certain symbol. And so the communication game or the meaning matrix of this, basically we have 18,000 program as columns, and then we have about 300 rows. And each one of them is a particular kind of input, which is a coordinate, and output is like what symbol you have on this coordinate. Yeah. And the communication game is as follows. We give a user a particular grid to communicate, and the user would reveal to the system of certain coordinates of like what is the content of those coordinates. And then the robot would try to infer the program, or rather basically the entire grid, from kind of a partial observation of this grid, right? So given 3 examples, like what kind of program do you think that you have in mind? Okay, and so let's do something high risk, which is a demo. Okay, so here we have some grid, right? So I'll kind of flash you through a few grids. So this is roughly the distribution of programs we can kind of communicate. Okay, so let's just try this one. So maybe tell me, if you were to communicate these kind of grid to the robot, like what are some well-chosen examples you might show to the robot? I guess, yeah, just talk to me over.
Looks like you want to give that whole box, right? And then maybe it's the inside and the outside, but maybe you can get away with less. I don't know.
Okay, so sorry, is someone else say something?
Yes, it's a little bit interesting because there's no cost to communicating in this paradigm, right? So like it seems like it doesn't cost anything to just show the whole thing. No?
Yeah, that's true. But when we ran a mechanical Turk experiment, people kind of prefer to communicate corners, for example, right? Because it does require some clicks, right? So we can try that. Right, so after one example, this is kind of the normal program synthesizer sync is this one, and the pragmatic one sync is like this one. So let's try another one, which on the corners. Right, so it's almost right? And then so basically based off of this, like what example would be helpful? I guess you can tell me. We have to give it more example basically.
Probably on the bottom edge.
Yeah, that seems like a good. Yeah, okay. So see, so kind of and this is online, right? So you guys can play with the system and kind of give it a different example and see what the system would do. But the idea here is if you look at the blue pragmatic robot, it's giving you an output that match the target. But the white robot, which is non-pragmatic, which is kind of it's a standing for typical programming by example. It's not wrong, right? Like literally, it's not contradicting the example that you give it, but like this particular grid isn't what kind of you had in mind, right?
Wait, so I guess I'm a little confused. You gave the corners. I guess when you talk about this matrix M, I'm a little confused how the corners magically make that work. Was there some other stats model that went into this based on what mechanical Turk workers did or something, or is it just that matrix M thing that you were showing?
Yeah, so basically this fact about communicating corner is being kind of in the convention of the robot and makes it efficient to communicate with user kind of falls out of the matrix. That falls out from the fact that our DSL talk about rectangular patterns, and by running the RSA algorithm, the system, for the lack of a better term, kind of discover that corners are a good way to communicate efficiently. Does that kind of answer your question? Like this is not, we didn't baking any prior about corners or rectangle, it just kind of falls out.
Yeah, it's really cool, although I don't understand intuitively why that works with it, why that falls out of the, you know, the iterations on M, but it's cool.
But
Yeah, so
the priors are embedded in the DSL then now.
well, the prior is kind of a uniform prior. So if we look at this basically here are the kind of DSL, and then you can make some choices right into this DSL, and essentially for each like production rule, we just choose equal probability of taking one production rule versus another.
Right, but it's already talking about boxes and things, right?
Yeah, that's right. Yeah, that's right. So it's talking about boxes. And it turns out that if you have a kind of a domain, or rather you have a mini matrix with like boxes, an example that talk about box-like things, then corners are kind of, if you talk about corners to a literal listener, there are less way for the literal listener to make a mistake. And therefore, if you're a pragmatic listener is kind of thinking about that, the speaker is thinking that way, you will be able to know that, hey, when someone is talking about the corners, I should generate the boxes that are kind of flush with the corner. But that's all kind of inside the computation itself, and we didn't have to impose that.
So I guess the follow-up question, in the study, did the participants have an understanding of the DSL? Like how much were they told about it, if any at all?
Yeah, that's a great question. So we just showed them 10 examples of random program from the DSL. So they kind of have a big understanding of what that distribution might be. They understand it's like rectangular patterns, and then they can have like different colors. So essentially we show them a few randomly sampled of these guys. So they're like, oh yeah, there are grids and there are chickens and pigs, and they can take like 3 colors. And most of the empty spaces are pebbles. So kind of the user know that if you communicate the white pebble, it's not that informative, right? And our system know that computationally.
Right. So I mean, like, and this is kind of the point of RSA, is that you have a sort of symmetry sort of thing where like, well, except like, because like the user builds a model for what kinds of things the pragmatic robot is good at understanding. Right, that's part of the recursion.
It's a little bit uncertain. I think RSA just like, it happens to match human convention on this particular domain, and in general, it might not, right? And the work of understanding like, is RSA is just one of many models that kind of model human kind of communication phenomenon, right? And there's like a lot of other models, and RSA is actually not quite the right model. We're finding out, right? It's actually kind of like a big Swiss, but kind of maybe the takeaway of this is that, you know, anything's better than having no preference over one program or the other, right? So maybe that's kind of like, at least you can't just like, oh, 10 programs, they're all satisfied. Okay, like arbitrarily the first program in some weird order, right? Like as long as you don't do that, the user will find your system kind of easier to communicate with. I can make that clear.
Already it feels like the non-pragmatic robot is at a disadvantage because it's not making rectangles, right?
It is making rectangles, right? It's just making rectangle that's too big.
Right, but it was making like the example here was like making a bunch of like rows. Is that also captured by the DSL? Is that like just a bunch of rectangles?
Yeah.
Well, the blue robot is simply the white robot with a better score function. And so they're working over the same set of satisfying program. It's just the blue one kind of choose the right one over the other ones.
Yeah, because I presume the white one's just gonna choose the first one, the first smallest one that it finds, right? In whatever,
Yeah, or some weird way you might organize the space of program, right? The most upper left one, whatever that means, right? Like it could be fairly arbitrary. So it will basically organize it, if you will, right? By, oh, the first production is like this, and the first production is this, right? It will like pick like the first one in that syntactical sense, right? So that could be a order. Okay, cool. So
in the case that drawing the corners first will lead to the correct, I guess, result for the pragmatic robot? Because I saw that you drew the corners at the top left and then the bottom right.
yeah, so I think this is a question we can poke with it more, right? Like it's not always the case. Like if you show it like not the corners, it actually might kind of throw it off. So for example, if I do like something like this, it kind of doesn't know that you need to kind of like go outside to the corners, right? So this might already be kind of a weird trajectory. The robot might be somewhat confused, and then you might wind up using like more examples to communicate. So there's the idea is like these kind of behavior of efficient communication is somewhat emergent. So there's not a good kind of like declarative rule that you can use to just take a meaning matrix and kind of declare, oh yeah, for sure, like these and these phenomena would happen. Is kind of you need to run the kind of the RSA algorithm, and whatever falls out, you kind of do a user study to see if that roughly line up with how human would like to communicate. So this is a little bit of trial and error, which is maybe slightly unsatisfying, but as far as simulationist goes, I guess you really don't know what's going to happen until you simulate, right? So cool. All right, so let's continue. So what we had is like one instances of this system working relatively okay. So thank you, random Jesus. Though didn't make like I could go horribly wrong, right? I could go horribly wrong. And so what we did is to make sure it actually is consistent for everyone. So we have some human experiment where we recruited 48 participants that play the game like what we did, except we showed them like 10 game with a white robot and 10 game with a blue robot, but communicating over the same set of targets, right? And so overall, we have about 1,000 games from these people. And then we see that on average, the blue or pragmatic robot require less symbol to communicate. So less is better, right? So we were using maybe 3 symbols or 4 symbols to communicate the target grid, and that's about what we observed from the kind of participant on MTurk. And white robot kind of require more symbols on average. And this is how human communication efficiency as a function of time. So when they play the first game, they use some number of example to tell what the grid is. On the second game, they might be used less and less, right? And so the kind of the takeaway is that blue is kind of trends down, right? And so that means that being pragmatic already match human convention from the get-go, right? From the first game they play, they already use less examples. And it turns out that human can actually have some kind of learning over time, right? So as you play more game with a blue robot, the human actually perform better over time. And the last one is the most kind of the flat, honest one, which is that which robot you like better, right? And most people like the blue robot. So this is kind of pretty standard. Okay, cool. And so as a recap, so we have demonstrated over kind of a particular domain, right? Human communicate well with a program synthesizer that's built on top of the recursive Bayesian reasoning of rational speech act. Okay. And so now the idea is how do we scale that, right? How do you make it into like a bigger domain of programs? And so let's see what we're doing on time. Oh, okay, we have to go kind of fast. Okay. And so the idea is that exact RSA is quite intractable, right? So we've showed that this is over like a 2x2 matrix is okay to do these alternative normalizations. With some hack, right, I was able to scale that into like this fairly reasonably sized mini matrix. But in practice, we often have combinatorial space, right, where you have combinatorial space of program from some grammar, and then you have like all possible examples that you might give. So how do we take this and scale that into kind of a more realistic programming by example domain? And one kind of the ideal solution, right? Imagine you have like infinite money, right? What would you do to solve PBE if you have infinite money? What you do is you would get a lot of human, right? So you will hire a whole bunch of annotators, and then you give these annotators programs and ask them to describe the program using examples, right? And you get a huge kind of label data set of program example pairs. And then what you do is you could train a neural synthesizer that kind of do the reverse process, right? They would take in the examples and then they will output the program. And then at inference time, we'll use the same neural network that interact with users, and the user will give these neural net kind of examples. And then this kind of neural net will be able to enumerate over programs and we can check for consistency, right? So this is ideal. However, it's pretty clear that would be like very costly, right? And it kind of require a lot of different annotation per different domain, right? So what we can do to make this better is, so the idea is kind of using self-play to generate data. So what you can do is you can actually have two robots. One robot would be the speaker, right, that generate example from programs. And the other is the listener that kind of do the opposite process. And then what you do is you just set them up in this like self-play communication game. And if a particular program is successfully communicated this way, you could say, well, that is a successful game. I'm going to take that game and I'll kind of cache it into my data set, right? And then from this data set, we'll be able to train over the trajectories that were successful on to improve the speaker and improve the listener so they become more successful as you play more game with these two agents, right? So something that looked like this. But the danger of doing self-play this way is that the two robots would develop some kind of language in some loose sense, right? That's very efficient with each other, but human can't break into it, right? So the best example was from some kind of like, I think it's from Facebook, right? And then you could see how the language is kind of devolved into this like fairly unnatural sense that no human would be able to kind of communicate into the particular barrier that the robot have erected. And so what we have, the idea for this work is actually do something similar to self-play, but rather than using successful communication as a criteria to add to our data set, we inject a little bit of rational speech act reasoning in the data set generation. Okay. Cool. And so the important thing is the inner loop, which is to use RSA to bootstrap better data. And kind of the hope and dream of this work, right? This is, again, like a risk. We don't know. We have to see if that's true. But our hope is that if we generate data with RSA in mind, then the data that the agents kind of generate through self-play would kind of be similar to the data that we get by annotating it from a human. And so that if we train on these data, then we should expect to get agents that actually interact well with people. And so I will describe to you the inner loop, and it has two steps. One is to sample some trajectories using self-play. And the second step is improve these samples with RSA. And so this is a simplified version. This is not quite how it works, but I'll kind of explain to you what that is. Right? So what you have is you have a target program. You give the target program to the speaker robot, and the speaker robot will generate a whole bunch of candidate examples that it would choose to explain the target program. And then each of these examples can get passed into the listener robot, and then it will generate some candidate program. So from this example, it'll generate like this particular program. From this example, it will generate like this particular program, and so on and so forth. Okay. I need to update the graphics. And so after you get some candidate program and examples, what you do is you construct a small mini matrix, right? You kind of plop up your target program in here as one of the column as well. And then you just put all the other program that's generated by the listener robot as distractors. And then on the columns, you just have all the examples that the speaker robot has chosen to describe the target program. And what we have here is a small mini matrix, right? It's not the whole space of all programs and example, but over the space of the examples and program that the speaker and listener robot kind of would prefer in the game that they just played. And you just simply run the RSA algorithm, right? You do the alternative normalization on this matrix, and then you can derive a pragmatic speaker S1. And this S1 would essentially, you take the argmax of that, which is, okay, given this particular target program, this is the best example you can use to describe it. What we mean is that this example is most discriminatory with respect to a literal listener. So in that kind of sense from the RSA computation. And so we add this particular data into the data set, right? And so this is a little bit similar to kind of AlphaZero, right, where two agents play the game. They generate a lot of trajectories. Most of those trajectories are kind of useless, and you kind of pick the best one, and then you add that to the data set. So for us, since it's a cooperative game, is the example program example pair that like best from the RSA algorithm. Okay. And then we do iterative learning with this. And so in terms of iteration, we I should probably go a little bit faster, right, to have some time for questions. So, but the idea is like we initialize them with the classic neurosymbolic synthesizer. So you might be familiar with like decoder and robust fill. And so essentially literal program synthesizers, neurosymbolic program synthesizer on the iteration 0. And to in the inner loop with the iteration, we do the inner loop we just described, right? Generating some samples and using RSA to pick the most communicatively sensible examples. And as a termination condition, we actually collect a handful of human labeled program example pairs. And then we pretend that the human is actually playing the game with one of our listeners that we trained in the loop itself. And then we just measure accuracy on how successful is this particular robot at recovering the program from actual human data. And then we kind of use this as a stopping criteria to kind of stop the pair from going too much into their own little convention that they can't come back. Okay. And so we apply this to the structured regex domain. I think it's from E.T. Austin, or I think it's from this group. And so our mini matrix is from DSL regex, and essentially any string you want to use to describe this regexes. And then we have some demo you could play with, and then we also run a similar study. And kind of the key result is that we can see that our approach, which is kind of the orange line, even outperform a kind of a human fine-tuned data set. So this is kind of the ideal case. We actually go out and collected kind of 400 human labeled program to example pair, and we fine-tuned our model on top of that. And like we're able to actually get better performance at that, only using, I think, like 40 just for the stopping condition rather than in the training of the agents. And we generate our own data through self-play. And we beat the literal listener, which is the kind of the robust fill. So classic neurosymbolic algorithm. Okay. And so basically speaker become more human-like over rounds. Okay, so one of our hypotheses is that speaker become more human-like as you kind of train the self-play. So let's give you a kind of a qualitative example, right? So here is a particular regex, which is like 3 or more ones followed by 3 or more H followed by 3 or more ones. On kind of the 0th round of the communication game, the speaker would use this particular string to describe it, which, you know, is not technically wrong, right? It's some 1 and some H and some 1, right? But as you train this robot in these rounds for more, round 8 is using this string to describe this particular regex. So you can see it's kind of exaggerating the fact that, oh, it could be a lot more on the other side of the regex, right? And then in the other 2 is kind of like, okay, on the shorter side, it should have been 3, right? So this is, by self-play, they kind of discover these kind of convention. And this, I guess, I don't know if this is too much, but the idea is kind of like what's the work that's kind of put into this particular kind of research is we've done some amount of manual work, right, which is like few hundred lines of code, 1,000 lines of code, and like 40 annotated human examples, and the rest of the data are generated by the robot. So it's kind of like some kind of computation cost, right? And then we heavily leverage kind of pre-trained large language model that kind of just exists on the internet we got from Hugging Face. Right? Cool. And so I think we can stop here. The last one is just further amortization of the RSA algorithm. So the idea is rather than doing the RSA computation, we can actually use like ranking as a kind of a approximation to the recursive Bayesian reasoning. And it turns out that just having a ranking of hypotheses actually achieves, just go to the result. So in terms of performance, the green one is like a ranking based listener, which is a lot faster to run because it's literally saying, I like this program more than the other program. And you can see that it actually is able to match the expensive full inference of RSA from L1. And And in terms of time, it's like orders of magnitude faster because their ranking is much faster to run than the actual recursive reasoning that you can. Okay. And so as a recap, I would just try to summarize it. It's kind of a recipe to how to make pragmatic program synthesis work. So the first step is actually write your meaning matrix, right? Like what are your columns? Like what are the hypotheses you're trying to communicate? And what are the rows? Like over which space of utterance can you use to talk about these hypotheses? And then kind of do a human study on a small domain with a pilot, right? Have some friend play the animal grid game. And once I see that, oh, it actually worked on my friends, then I have a pretty good confidence I can scale this to like a bigger space, right? Cool, and that's it. So the first step is make sure it works for your domain, maybe like a simplified domain, right? And then you could think about how to scale that up. And these works I presented give you some fairly robust way of scaling it up to kind of fairly combinatorial domains. And future direction is maybe to echo what we had in the start of the meeting, which is like, what are some of the stuff we can put on the left-hand side? Well, it was actually kind of anything you could put here, such that through kind of the execution semantics of the program, you could get like 0-1 signal from it, right? So what are some of those? And you could use the execution traces, assertions, partial programs, like in context learning is actually like input output, right? But it's just for LLM. So it's kind of applicable in that as well. And on the more theoretical side of modeling RSA, I didn't get to it, but like we've shown that ranking is actually quite a powerful way of approximating the behavior of the recursive Bayesian listener. And so there might be some alternative account for how human have efficient communication that's not based on RSA and recursive reasoning. It might just be some kind of distilled ranking of things over time. Okay. That's it. And here are the people. So most of the work is done over Zoom. So I was finally able to actually meet these people like face to face in real life. And that happened last month. So I'm pretty grateful. Priya and Lina, I met them in Boston at some point, but yeah, those are the people behind both of these works. And that's it. Thank you. Yeah, that's it. Could maybe still have some time for questions. Yeah, please.
So you talked about using ranking and I guess when you first talked about the RSA algorithm, how it works, I immediately thought, oh, it sounds a little bit like TF-IDF or something like that, a ranking thing. But like
yes.
TF-IDF, you have to do, there is a global step where you have to look at everything. And so what kind of ranking are you using? Are you doing something like TF-IDF? Because I don't think TF-IDF would be orders of magnitude faster. It might be faster.
Yeah, that's right. That's right. Okay, so you said a lot of like insightful things. So first of all, TF-IDF is a form of pragmatic reasoning. So in the pragmatic that we did is we have M that goes into, we normalize the row first, we get L0, and then we went up to S1, and then we went up to L1. So that's a way you can climb the recursive reasoning ladder. TF-IDF is roughly similar to from M, you have S0, and then to L1. So this is roughly speaking the kind of the recursive reasoning that TF-IDF did. And this is a kind of reasoning that we did. In practice, those two may be actually quite similar. So that's the answer to TF-IDF. The kind of ranking that we did is a, yes. So the RSA ranking is actually example dependent, right? So the idea is that upon seeing these utterances, I might have some kind of ranking of program. And upon seeing different utterances, I might see a different way of ranking program. And they actually might be inconsistent, right? So on this utterance, I might rank this one over this one, but on some other utterance, I might actually rank this, like the ranking might swap, right? And the approximation that we were making is example agnostic. So we actually have a single ranking independent of any example, which says, I just always prefer this over that, over that, right? Just like kind of a global ranking of program. And the way these kind of synthesizer work is that it will use the meaning matrix M, which is kind of execution consistency, to filter out, like given an utterances, these are the two programs that literally matches it. And then it uses a global ranking to pick, like I would choose this one over the other. So that is just the right ranking for this game, right? You could imagine this game, you want to choose the smallest shape
Is that what your ranking actually shows was, is the smallest your ranking?
Come again?
So what was it, what is the ranking you ended up using? Is it like smallest program as the way to rank them?
If you were to hard code a rank of using the smallest mass of grid as the heuristic for this domain, it will align quite well with the pragmatic listener, which through computation rediscover a similar ranking. It's not that ranking, but it's like similar to it.
I see, so it's domain specific, you kind of tried several different rankings and found one that seems to match it.
Yes, but what you can also do is you could actually use, so I didn't get to this part, is what you can do is you could use RSA to generate kind of a data set of how L1 would like to rank these programs, and you can later down, you could like distill that out by doing some kind of like annealing or neural ranking learning function to, you could distill a global ranking that's consistent with the example dependent ranking of L1. And we actually, that's the approach that we use to get these kind of approximation that doesn't do the RSA inference, but it's like really fast.
I see, okay, you generated a bunch of potential examples and then use that to train a neural thing that would kind of figure out which ranking was most consistent with all of those examples.
Yeah, so think of this as like it's kind of like a compilation. So we have a slow RSA algorithm. We run the slow algorithm with a pragmatic speaker and a pragmatic listener. We let them play a game with each other. We get a whole bunch of data, and then we see like from these kind of example dependent ranking, can we distill a single ranking that's as consistent to that sets of partial ranking as much as we can.
Right, yeah, thanks.
Yeah.
I have a question. So, one of the limitations of RSA is that it's less about human conversation and more about like humans sequentially announcing things to each other, right?
Yeah.
Like, for example, like I think on average, like people engage in like conversational repair, like every minute or two, right?
That's right. That's right.
And so like, for example, so in your example with the glasses and the hats, like when you said glasses, I was actually thinking that would be ambiguous, but I would say like, I would say something, but then also ask to clarify. And so I wonder, I mean, I think it seems like using RSA means that like it kind of puts you in the box of like the user is only supplying examples, but the system cannot ask for anything.
Yeah.
And you could get pretty tremendous improvements if you could figure out ways of having the system ask for examples that would be particularly disambiguating. That makes sense, right?
Yeah, that totally makes sense. And this is something that Sargis is maybe going to explore in his thesis. So there are different ways of resolving ambiguity, right? The way of RSA is actually by some kind of convention, right? It's like, I would just prefer this over that given these kind of utterances, but there's other way of resolving ambiguity, like one you said, which is like repair, and the other one is like ask clarifications. With respect to kind of asking question, like the agent asking question, a kind of comparison you can do is active learning, right? So in the active learning regime of programming by example, the user don't choose the example to tell the robot, right? Like I would like these test cases. The robot will actually ask the user, hey, given this input, what the output ought to be. And you can actually show, is this in my backup slide somewhere? Yeah, so in active learning, the synthesizer proposed the input and the human actually gives the output, right? And it turns out that RSA, because the human choose both the input and output to show to the system, there's like the information content over these kind of utterances is actually like much greater because you know the right answer, you're choosing the one to explain the right answer. And when the system is asking, oh, should it be one? The best the system can do is some kind of like a bisector, right? Like one way or the other. But if you are choosing the example, you could choose the non-bisector. You could choose like the crazy, like you could say like that's very specific, right? So it's the kind of the plain 20 question, right? Your first question would be, does it fly or not? But if someone's just trying to tell you the hypothesis, I would just say, oh yeah, the animal have 8 legs. And you're like, it's a spider, right? And then so it become like one question, right? So that's the kind of the difference. And so that's why RSA is actually quite powerful because you that's kind of like the user give both. Yeah.
Right, thanks.
Yeah, I think these things are like super cool. I mean, it's like, yeah, it's great. Cool. That could be it, or not, or it.
Yeah, I don't know. Yeah, I think we're good. Yeah. Well,
Okay,
thanks
sounds great.
for coming.
Yeah. Give me the recording. I guess I could put it on my YouTube or something. Maybe get
Yeah,
like
yeah.
1,000 likes or something.
Yeah, for sure, for sure.
Cool.